You ever just look at a massive bridge, or a skyscraper, or even something as simple as a shelf bracket and think, how in the world is that thing not falling down? I mean, really. It turns out our entire world is held together by this constant, invisible battle of forces. Pushes and pulls, tension and compression. So in this explainer, we're going to pull back the curtain and take a look at that hidden world.
All right, let's get right into it. For the next few minutes, I want you to put on your engineer's hat with me. We've got a job to do. We're going to analyze a real live structure and figure out if it's actually strong enough for the job it's supposed to do.
And here it is. Now, I know it looks pretty simple, right? But trust me, this basic setup is the foundation for countless real-world designs. So what we've got is a horizontal boom, we'll call it AB, and an angled rod, BC. They're both pinned to a wall and to each other. Now, its one and only job is to hold up a massive downward force right here at point B, 30 kilonewtons. To put that in perspective, that's almost 7,000 pounds. It's like hanging an entire pickup truck from that one single point.
So that leads us right to the big high-stakes question, the whole reason we're here. We have to know for sure. Is this design safe? Is it going to hold? Or is it going to fail spectacularly? Well, let's find out. Okay, so to get our answer, we've got to become kind of like structural detectives. See, the most important forces in this whole thing are the ones you can't even see. They're the internal forces, the ones squeezing that boom and stretching that rod. And our first mission is to find them. So how do we do that? Well, the very first thing any engineer does is draw one of these, a free body diagram. It's a game changer. What we do is we basically just get rid of the wall, and we replace it with arrows that show the forces the wall was putting on the structure. Now, I know it might just look like a simple sketch, but this little diagram is an absolutely crucial tool. It lets us turn a messy, real-world problem into a clean math problem that we can actually solve. You know, this entire analysis hinges on one really beautiful, simple idea: static equilibrium. I mean, think about it. The structure isn't flying off into space, right? And it's not crashing to the ground. That means all the forces acting on it have to be perfectly balanced. Every push-up is canceled out by a pull-down. Every force to the left is matched by a force to the right. It all adds up to zero. Simple as that.
Okay, now this is the cool part. This is how we actually use that principle. We can just zoom right in on a single point. An engineer would call it a joint, like point B here. We know we've got that 30 kilonewton force pulling straight down. So for that single point to be in balance, the force from the boom and the force from the rod have to work together to push back up and cancel it out. And what's awesome is they form this perfect closed triangle. Just like that, we've turned a physics problem into a simple geometry problem. So cool. And once we solve that triangle, boom, we get our answers. We've uncovered those hidden forces we were looking for. Turns out the boom, that's AB, is getting squeezed with 40 kilonewtons of force. That's compression. Meanwhile, the rod, BC, is being stretched with 50 kilonewtons. That's tension. So, great, we have the numbers, but so what? What do these numbers actually tell us?
Yeah, knowing the force is really only half the battle. Think about it. A 50 kilonewton force might be absolutely nothing for a huge, thick steel cable, but it would instantly snap a tiny little wire. So to really understand what's happening inside the material, we have to talk about probably the single most important concept in all of mechanics: stress.
So let's circle back to our question. We found 50 kilonewtons of tension in that rod. Is that a lot? Is it a little? Well, the answer is it depends. It depends entirely on two things: how big the rod is and what kind of material it's made from.
And that right there is exactly what stress is all about. See, it's not just about the total force, it's about the intensity of that force, spread out over a certain area. I love this analogy. Think about your own body weight. That's a force, right? Standing normally on 2 feet is no big deal. But what if you tried to stand on just one tiptoe? The force, your weight, is exactly the same, but the area is now tiny, so the stress on that one point would be absolutely enormous. That's why the formula is so key. Stress equals force divided by area. And you can see it perfectly right here. That 50 kilonewton force isn't just yanking on one single point. No way. It's spread out evenly across the entire circular face of that rod, what we call the cross-sectional area. And stress, well, stress is just the measure of that internal pressure that the material is feeling on the inside.
All right, this is it, the moment of truth. We have all the pieces of the puzzle now. We know the force in the rod is 50 kilonewtons, and we know from the plans that the rod has a 20-millimeter diameter, which means we can easily calculate its area. It is time to put it all together and get our answer. So we plug it into our formula, force divided by area, and we get our number. The stress inside that rod is 159 megapascals. That is the actual real-world internal pressure that the steel is fighting against right now.
But again, a number by itself doesn't mean anything, right? 159. Is that high? Is that low? Are we super safe, or are we getting dangerously close to the breaking point? We need a yardstick, something to compare it to. And here's our yardstick. See, every single material, I don't care if it's steel, wood, plastic, whatever, has a limit, a breaking point. And what engineers do through tons and tons of testing is they figure out a safe, allowable stress. This number already has a safety factor built right in. And for the particular type of steel in our rod, that safe limit is 165 megapascals.
So here we are, the final showdown. On the left, we have the actual stress that our rod is feeling right now under that load, 159 megapascals. And on the right, we have the absolute maximum stress the material is allowed to handle, 165 megapascals.
And just like that, we have our answer. The structure is adequate. Because 159 is less than 165, the rod is not going to fail. Now, it's pretty close to the limit, for sure, but it is on the safe side. Our analysis is done. The structure will hold.
But, this whole process isn't just about checking if stuff that's already built is safe. These exact same principles are what let engineers design brand new things, right from scratch. So let's kind of zoom out for a second and look at the bigger picture. Okay, so what we just did, that's called analysis. We were handed a finished design, and we answered the question, is this thing safe? But the other side of that coin is design. And that's when an engineer starts with a blank sheet of paper and says, okay, I need to hold up this big, heavy thing. What material do I use? How thick does my rod need to be? It's the same math, the same principles, just flipped around to create something new. And that really is the heart of the matter. This quote just nails it. The entire field, this whole subject of mechanics of solids, it exists for one reason: to give engineers the tools they need to both analyze and design all the load-bearing structures that make our modern world possible. So the next time you're driving across a bridge, or sitting in a huge stadium, or maybe just looking up at a skyscraper, I want you to just take a second. Think about those hidden forces, those invisible stressors, all perfectly calculated and balanced inside every single beam, every single cable. It's this silent, constant battle that's happening all around us. And now, you know how it's won.